Okay, this is Keeper 2.4, one-sided limits. Find the limit graphically. So we're given the function g of x equals the absolute value of 3x over x. We want to sketch this graph and then using our graph, evaluate the limits a, b, c, and d over on the right side. So absolute value of 3x, that means that this numerator could be 3x or it could be negative 3x. So you could write this as a piecewise function like we did in Unit 1. And we're going to separate this. G of x equals, I have 3x over x and negative 3x over x. Well, if I simplify that, I have 3 and negative 3. So this function is actually a piecewise function that's two horizontal lines. So I need to see where the domain is going to be for g of x equals 3 and what the domain is for g of x equals negative 3. So let's look at some x values that we can plug in. So if I was going to make a table, and maybe I'll do that right here. Let's start with 0 and put it in the middle so I can have some positive and negative values. If I plug in 0 for x, I have the absolute value of 0, which is 0 over 0. 0 over 0, that doesn't exist. Okay, now let's try a couple of positive and negative x values, see what happens. So plug in 2, absolute value of 6 is 6. 6 divided by 2 is 3. Plug in 1, and you get absolute value of 3, which is 3 over 3, or sorry, 3 over 1, which is 3. Now plug in my negative 1. Absolute value of negative 3 is 3. 3 divided by negative 1 is negative 3. And then absolute value of negative 6 is 6. 6 divided by negative 2 is negative 3. And this is going to continue no matter what values I choose for x. So you can see where the domain is changing. Let's see if I can go to my eraser here. This is the absolute value of 3x over 3 simplified to be positive 3. And that domain is when your x is greater than 0. And g of x equals negative 3 when x is less than 0. So let's sketch this. 1, 2, 3. It needs to be open. Horizontal line at 3. 1, 2, negative 3. So this is the way that absolute value functions will behave when they're set up like this inside of a rational function. And so what you can do is simplify this like we did to start with. It's 3x over x, which is 3, and it's negative 3x over x, which simplifies to negative 3. So I have these two horizontal pieces to this function, and then you need to look at the domain where it works. So evaluate, looking at this graph. The limit of g of x is x approaches 0 from the right. So from the right, approaching 0, that's going to equal 3. The limit of g of x as x approaches 0 from the left is -3. The limit as x approaches 0 from both sides, well, if you're approaching 0 from both sides, from the left it's -3 and from the right it's +3, so that does not exist. Remember, do not put equals. Does not exist. That's really important, that it can't equal something that doesn't exist. And then the last one is g of 0. So what is the y value when x is 0? It does not exist. Take a look at this next example. H of x equals the square root of x minus 2. You should know what square root functions look like. It is really important that you know all of your parent functions and transformations. So in the future, you're able to just visualize the function or do a quick sketch of the function to be able to evaluate your limits. So this is a square root graph that has a transformation of right 2 places. So something like that. And now I can evaluate these limits. The limit of h of x is x approaches 2 from the right side. So if I'm moving from the right side on the graph, so you'll want to trace your graph, you'll see that it is approaching the y value of 0. The limit is x approaches 2 from the left side. If I'm on the left side of 2, the graph doesn't exist. No, does not exist. Remember, don't put equals, does not exist. These are really important things for AP test. And C, the limit as x approaches 2 of this graph h of x. That means from both sides, since the left and right limits aren't the same, then this also does not exist. And then the last one, h of 2. So the point where the x value is 2 on this graph has a y value equal to 0. This next slide is a piecewise function, and we're going to evaluate limits for it. So it's really important that you are paying attention to the domains in the piecewise function. So for A, it's the limit of f of x as x approaches 3 from the right. So the x values that are on the right side of 3 are when x is greater than 3. So that means I'm going to be evaluating this part A by looking at the third piece of the function, the 14 minus x squared. So I'm going to plug into 14 minus, and I have 3 squared, and that's because it's from the right. From the right means x is greater than 3. 14 minus 9 is 5. Part B, evaluate the limit of f of x as x approaches 3 from the left. The left side of 3 is the x values that are less than 3. So that's going to be the first piece of the function. Plugging it into x squared minus 16. And my x value is this 3. So 3 squared minus 16. 9 minus 16 equals -7. C, the limit of this function f of x as x approaches 3. That means from both sides. And looking at part A and B, you see that the limit from the right is 5. The limit from the left is -7. Those do not equal each other. So this does not exist. No equals there. And f of 3. So where does this function actually exist when x is 3? And so if I look at the middle piece of the function, it says f of x equals 5 if x equals 3. So that answer is 5. Now, we're going to find the limit of these two problems algebraically, but we're still going to think about the graph. We're just not going to actually graph it like we did earlier. So A, you want to find the limit of 3 over x minus 2 as x approaches 2 from the left. This is a rational function, and I know with a rational function, I need to look at the denominator for vertical asymptotes. Sometimes I also need to see if there's a hole in the graph. So I have a vertical asymptote at x equals 2. So if I think about this graph, I know that x isn't existing at 2, but I can see what happens on the left side of 2. I'm just going to do a little sketch and draw in your vertical asymptote, and that's at 2. You should also know horizontal asymptote rules, and the degree in the numerator is smaller than the degree in the denominator. So you have a horizontal asymptote at y equals 0, which isn't going to show up. But I'm going to do a quick sketch of what this function should look like. And so now I want to find the limit as x is approaching 2 from the left side of 2. And so I can follow that, and that is approaching negative infinity. Okay. B, we have absolute value. So we already talked and looked at an absolute value function inside of a rational function and how that created a piecewise function. So we're going to do the same thing here. Start by factoring it if you can, which we can in this problem. Since I'm just simplifying this limit, I've got to keep writing the limit as x approaches 5 from the left. I'm going to factor out a negative 3 from the numerator. And I'm going to also rearrange those terms. So that leaves me with x minus 5. And then in the denominator, I'm going to factor out a 4. And I still have my absolute value of x minus 5 right now. Okay, so we want to find the limit as x approaches 5 from the left side. So since it's from the left, we want to, let's write this out again, limit as x approaches 5 from the left. This absolute value, you know, that could be 4 times x minus 5, or it could be 4 times a negative times x minus 5. And since it's from the left, this is going to be the negative version of it. So I've got negative 3 over x minus 5. That stays the same in my numerator. But since it's from the left, this is a negative 4 x minus 5. If this was from the right, it would stay positive 4. I wouldn't need to change the sign. The x minus 5's cancel. Negative 3 over negative 4 equals 3/4. C, another problem that was just like that. This one's actually a little bit easier because we don't need to factor anything. So we are looking at the limit of the absolute value of x minus 2 over x minus 2 as x approaches 2 from the right side. So if you were going to rewrite this function as a piecewise function, you would have x minus 2 over x minus 2, which simplifies to be 1. And then you'd have negative 1 times that x minus 2 over x minus 2, which simplifies to be negative 1. So my answer is either going to be 1 or negative 1. So if you think about these, you can just simplify the expression, and you know that your answer is either going to be that positive number or the negative number, depending on whether it's coming from the left or from the right. And since this is from the right, then this equals, there, got my pen going again, equals positive 1. So I didn't need to simplify that or work that out, but I needed to know what that function looked like. And D, we have a square root function. It has a negative x, so that means that this function is reflecting over the y-axis, and you have a horizontal shift. So you can do a quick sketch. So if I did that, it would look, oops, sorry about that. There we go, something like that. And that's 5. So know your parent functions, know the transformations. And I want to evaluate this as x approaches 5 from the right side. This graph does not exist on the right side. So that answer is does not exist.